Okay, so let's take a look at the proof of Euclid's proposition number 35. Namely that if we have two parallelograms that happen to share the same base and their opposite sides are along the same parallel lines, then those two parallelograms have the same area to them. And so kind of the setup that we're looking at, we have one parallelogram here, A, B, C, D, and we've got another parallelogram here that's going to be B, C, E, and F, and those two parallelograms share a base, and the sides opposite that shared base are on the same line. Now we want to show that those two parallelograms have the same area to them. So how do we go about doing that? Well, one thing from our previous proposition, our previous homework problem, which was actually Euclid's proposition number 34, was that when we have those parallelograms, that the opposite sides are going to be congruent. So we've got side AD congruent to side BC, and we also have side BC congruent to side EF. Now, what that means is that by our common notion number one, that side AD is going to be congruent to side EF. Now, what we also have from that proposition was that side AB will also be congruent to side CD, because those are opposite sides of the same parallelogram. Okay. Now kind of taking this little segment in the middle, since AD is going to be congruent to EF, then we can take this little segment DE and add it on to both. So if we look at the segment AE, which is just AD plus DE, then that's going to be congruent to the segment DE plus our segment EF, so our segment DF. So what that really tells us then is that this longer side from A to E is going to be congruent to this side from D to F. So now kind of looking at these angles here, because this line DC is going to be parallel to this line AB, it means that these two angles, the angle at EDC is going to be congruent to angle DAB. And so from there, what we actually have with that is that our triangle here is going to be, our triangle AEB is actually going to be congruent to our triangle DCF. Okay, now why is that going to be the case? Well, we said that AE is going to be congruent to DF. We know that AB is going to be congruent to CD, and we know that these two angles in between are going to be congruent because they're corresponding angles for parallel lines. And so what that means is that triangle ABE is going to be congruent to triangle FDC by our side angle side congruence theorem. Now, what we want to do is kind of looking at those two triangles. Well, we notice that there's this little area of overlap there. And that area of overlap, if we kind of take out that triangle DGE from both of those triangles, then it means that the areas, since those two triangles are congruent, they've got equal areas. And so if we kind of take out the same magnitude from each one of those, then the remainders are also going to have the same magnitude. And so the areas, when we take out that triangle from both of them, will also be the same. And so what that really means is that if we look at these two trapezoids, so we've got this trapezoid ADGB, which we get from taking that little triangle out from the bigger triangle. And if we look at the trapezoid here, EGCF, then because those started out as congruent triangles, so they had the same areas, we took out the same area, it means the area of these two trapezoids are actually going to be the same. Okay. Now, if we kind of take this one step further, now look at this triangle, GBC. So if we take that triangle and put it back in to each of the two trapezoids that we have, then what we obtain, taking this triangle, GBC, and putting it into trapezoid ABGD, actually gives us our original parallelogram. And so likewise, if we take this triangle GBC and put that into our trapezoid EGCF, that gives us our second parallelogram. And so because the areas of the two parallelograms are equal, then we add the same amount to each trapezoid, to the areas of each trapezoid, so those two areas have to be equal, and therefore the areas of the two parallelograms must also be equal.